Hello, physics students. This is Mrs. Krumschrader, and we are looking at this concept development practice page 2.2. If you just want to do this with me and then turn it in when we're done, that would be great. So it's kind of up to you. So number 1, Nellie Newton dangles from a vertical rope in equilibrium. Therefore, the sum of the forces is equal to 0. The tension in the rope, the upward vector, has the same magnitude as the downward pull of gravity, the downward vector. So, right, this is, and I just want to kind of measure this so that I know, right? This one is, I'm going to call it 3 centimeters long, and this one is 3 centimeters long. And so this is just telling us that this is her weight of Nellie Newton. And this is that tension in the rope, which is our support force. Okay. So, and Nellie's weight isn't going to change. So this is 3 centimeters, and this was 3 centimeters. So number 2. Nellie is supported by 2 vertical ropes. Draw tension vectors to scale along the direction of each rope. So this should still be 3 centimeters long, which it is. So this is her weight, and this is 3 centimeters, representing, maybe we'd say 300 newtons. Okay. And so I have 2 ropes, right? So it's going to be half of her weight. So half is 150 newtons, and half of 3 centimeters would be 1.5 centimeters. So there's my, here's my 1.5. So there's my vector. Okay, and I'm going to do the same thing over here. So 1.5. There's my vector. Okay. So these would be 1.5 centimeters in length, and they would be 150 newtons each if I assume that her weight is 300 newtons here. So, number 3, this time the vertical ropes have different lengths. Draw tension vectors to scale for each of the 2 ropes. It's still 300 newtons is her weight, and this is still 3 centimeters long. So I still just have 2 ropes that are equally supporting, so I still need each of these to be, okay, a centimeter and a half. So to right there, and a centimeter and a half right there. So these would be 1.5 centimeters each, and they would represent 150 newtons each if her weight is 300 newtons. Question number 4. Nellie is supported by 3 vertical ropes that are equally taut but have different lengths. Again, draw tension vectors to scale for each of these ropes. So her weight is still 300 newtons, which is 3 centimeters in length. But this time I have 3 different ropes. So it's going to be 1/3 of her weight, which is 100 newtons. And 1/3 of 3 centimeters would be 1 centimeter. So there's 1. There's my second. And there's my third. Ooh, that one's off a little. That wasn't a very good measurement. go. There's my third. So those would all be 1 centimeter in length. So question number 5, we see that tension in a rope is blank, the length of the rope. So what they're asking here is, did our tension in the ropes depend upon the length of the rope? Well, the spot where we can do that comparison is here and here, correct? Did the tension matter of how long that rope was? No. So it is independent of the length of the rope. So the length of a vector representing rope tension is blank the length of the rope. It is also independent of, because it does not depend on how long that rope length is. So I asked you just to do pages 5 and 7. So here's page 7. Sorry about that. Vectors and equilibrium. The rock hangs at rest from a single string. Only 2 forces act on it, the upward tension T of the string and the downward pull of gravity W. The forces are equal in magnitude and opposite in direction. So remember, that's telling us that this is in mechanical equilibrium. And would this be static or would this be dynamic? Right? This would be static because it's not moving. Okay? So the net force on the rock is what? Well, if I have equal tension and weight, then they would cancel each other out when I subtracted them, and my net force would be 0. And I also know my net force is 0 here because remember, when there's a net force, the object is moving. And this rock is just hanging there. So I also know, like, it makes sense that my net force would be 0 here. Here the rock is suspended by 2 strings. Tension in each string acts in a direction along the string. We'll show tension on the left string by vector A and tension on the right string by vector B. Right? So there's vector A, there's vector B. The resultant of A and B is found by the parallelogram rule and is shown by the dashed vector. Note it has the same magnitude as W, so the net force on the rock is. So let's talk about how they got this resultant here. Right, here's A, and so again, I draw this line and I have these 2 lines that are parallel to each other. And I have these 2 lines that are parallel to each other. And then I go from my starting point to my diagonal point, and that is my resultant. So remember, this is my resultant R. Okay? So note, it has the same magnitude as W, right? So W and this resultant R are equal in magnitude or size. They're opposite in direction. So the net force on the rock is 0, right? So again, this is in mechanical equilibrium. It would be static equilibrium because the rock is not moving. Consider strings at unequal angles. The resultant A plus B is still equal and opposite to W. So this is our W, and this is our resultant A plus B. Okay. And is shown by the dashed vector. Construct the appropriate parallelogram to produce this resultant. Show the relative magnitudes of A and B. So what we're being asked to do is kind of take this and move parallel and draw that parallel line, and then do the same thing with B. Okay, so line my ruler up, move parallel. There's that other side, right? And now we know there's my vector A. Here's my vector B. So, okay, we're showing the relative magnitude. So is the tension in A or the tension in B greater? We can tell that the tension in A is greater because the vector is longer than the vector in B. So tension in A is greater than tension in B, and that's because vector A is longer than vector B. Repeat the procedure for the arrangement below. So now they're saying, here's my weight, here's my resultant of A plus B. So draw our parallelogram. So again, we do the same thing. We want to be parallel to B, kind of slide over. We're parallel to B. We want to be parallel to A. So we slide over. And again, here's my vector A. Here's my vector B. So here, tension is greater in vector B. And how do we know? Again, because vector B is longer than vector A. So no wonder hanging from a horizontal, tightly stretched clothesline breaks it. So, this last one. Construct vectors A and B for the cases below. First draw vector W, then the parallelogram that has equal and opposite vector A plus B as the diagonal. Then find the approximate magnitudes of A and B. So I'm going to choose to make these all 1 centimeter. So I'm going to say that the weight of this rock has a vector of, or a length of, 1 centimeter. So there's my weight. Now, again, I have to have a vector, my resultant, that goes up 1 centimeter, right, and ends right there. So that's my resultant of A plus B. So now I want to do the parallelogram. So here's A. I slide over. There's my side A. Here's B. Slide over to the top of my vector. There's B. So here's my vector A and vector B. And those look about the same, right? So A is about the same as B. So we'll do the next one. Our weight is still not going to change. So I'm going to kind of try to do it a little bit more quickly. Putting my 2, and I'm going to go down 1 centimeter. And I'm going to go up 1 centimeter. Okay, so here's my weight W. Here's my resultant A plus B. So now again, I do the same thing. Oh, here's my A. Here's my B. Here's my vector A. Here's my vector B. Comparing, right? what's happened to the tension in our ropes? Is the tension in this situation number 1 or the situation number 2 greater or less? So hopefully, again, because we're being careful with measuring here, the relative lengths of these vectors show the relative tension in these strings. So notice the tension in situation 2 here is higher than the tension in the ropes in situation number 1. So now we have situation number 3 down here, right? I'm going to do the same thing. Okay. Trying to make sure that in the video though. So I'm putting my 1 centimeter, go up 1. Oops. Should have moved it. There we go. Go down 1. Okay. So this is my resultant, A plus B. This is my weight. So now I have to do the parallelogram. And these are like this. So and then same thing here. So here's my vector A. Here's my vector B. Okay, so there's A and B. And again, what's happened to my tension? My tension here is much, much higher. Remember when we did the notes the other day, or I think it might have even been just yesterday, we talked about that as this angle here gets bigger and bigger, what happens to the tension in my ropes? It goes up, right? So this bigger angle, we have more tension in the rope. Now, for those of you who are kind of going above and beyond here, right? You just had to do pages 5 and 7, but filling in the magnitudes for the net force of each case, right? These are equal in size and opposite in direction. So my net force would be 0 newtons. Here, if this is 4 newtons and 3 newtons, again, then I would be 1 newton and to the right. Now, this is a special triangle, but we can still do our resultant, right? We would just kind of basically make our parallelogram, and then our resultant is there. So this side is 3, this is 4. So that's where we're going to use that Pythagorean theorem, right? 3 squared plus 4 squared equals our resultant squared. So our resultant is the square root of 3 squared plus 4 squared, which is 25. 9 plus 16. And the square root, not the square root of 25 is 5, which you probably do. Now, you guys, is it really going to change anything here? Not really, right? It's going to change the direction, but the magnitude is going to be the same. But mathematically, I'm still doing 3 squared plus 4 squared and taking the square root. So it's 5 newtons. It's just in a different direction. Like if we used north, south, east, west, right? We would say this one is 5 newtons northeast. we would say that this one is 5 newtons southwest, okay, for our direction. Now this one, it looks like it would be really kind of hard, right? But these two are in opposite directions. So that means that my resultant here is only going to be 3 newtons. So maybe about right here. Okay. So again, I draw my parallelogram. I get my resultant. And this was 3, that's 4, so this is that 3, 4, 5 again, so this would be 5 newtons, and again we'd say it's probably northeast. And this one again is going to be the same thing, right? This time it's going to be 3 newtons down. So there's that. Here's this. Here's my resultant. And again, it's a 3, 4, 5, so it's a 5 newtons, and we'd probably say southwest. This one, right? So again, my parallelogram. My resultant. And this is 7 and 7, so I'm going to do, my resultant's going to be the square root of 7 squared plus 7 squared. Okay. So second square root of 49 plus 49, right? 7 squared is 49. And so it's about 9.89. So we'll just say, right, the 8 would make that 10. So we'll say about 10 newtons. And again, it would be northeast. Notice, you guys, again, this is going to end up being the same, right? Because 10 minus 3 is going to be 7 newtons, right? So I'm going to get that same thing again with my parallelogram. So here's my resultant. So it's going to be about 10 newtons again, but this time it's going, and it's northeast again even, same direction. These two are more complicated. So on the key, there's the answers to them if you want to try them, but these are not too bad. So if you don't mind math, these might not have been too bad for you to do. So have a great day, and I will talk to you again soon.